Okay, hi everyone. Thank you for joining us for this product preview on AI-based physics predictions in your web browser. I'm Steve, and I'm going to be your host today. I've got the pleasure of hosting this webinar. I lead the application engineering team and the partnerships program here at SimScale, and I've got the pleasure of introducing Jakob and Richard as the main speakers today. So Jakob is a product manager at Navasto. He has a PhD in aerospace engineering, and he's committed to advancing machine learning integration into industry simulation. So the perfect person to be talking to us and partnering with us today on this amazing product introduction. And on the SimScale side, I'm joined by Richard, sat next to me. He's our product manager for AI at SimScale. He's got a mathematical and mechanical engineering background. And Richard has just celebrated his 10th year in SimScale. So a couple of bits of housekeeping before we get started. You will remain muted for the entire of this presentation, but if you have any questions or comments, please feel free to use the chat to speak to the organizers or the question functionality to send questions in as we go through. You'll find these options on the GoToWebinar panel. You may need to click the little arrow to get the drop down and then answer your questions. Okay, so let's get started and have a look at the agenda for today. Okay, so let's get into it. As an engineer myself, I'm extremely excited by what we're presenting today. AI and machine learning are really going to shake up the way that we design products. The traditional design cycle where you do all of your simulation at the end is really going to change, and I think we're going to see a big advancement. I was talking to some colleagues about this the other day, and I really think AI is going to do for engineering what the internet did for engineering when it came in a couple of decades ago. So I'm really excited to present to you what's happening. The collaboration that we've got here with Navasto means that SimScale and Navasto are going to be bringing to market the first fully integrated cloud-native AI-based physics prediction platform. It's the first simulation service like that where any engineer is going to be able to come in and use an AI-based physics prediction to get instantaneous results on a simulation. And we're making this available to everyone that uses SimScale. That's one of the most fascinating and incredible things about what we're doing here. It's really going to bring this kind of capability that used to be based only on massive servers in big organizations. It's going to bring it to the masses. So the agenda that we're going to go through today is we're going to introduce the two solutions, SimScale and Navasto. Richard will then go through a bit more detail on why we've decided to go down the route we have, why we've partnered with Navasto, and how we're going to bring this technology to you today, and also the next steps that we're going to make in the development. We'll have an introduction to Navasto from Jakob and why this is so important and how they're actually developing the AI-based machine learning algorithms. We'll have a live demonstration of the software, and then we'd be very happy to answer any questions that you've got and talk about the early access program, how you can get your hands on what we're going to show you today. So first of all, before I hand over to Richard, I'm going to go through a very short overview of SimScale. In case SimScale is new to you, I just want to talk to you why SimScale is different from the traditional tools. SimScale is completely cloud native. This means all you need to access and run SimScale is a web browser and an internet connection. It's truly a SaaS cloud-based simulation platform. And this is the same for the AI result preview that we're going to be looking at today. SimScale is one integrated broad physics platform. There's one UI. You don't have to switch from a different tool if you want to do CFD analysis or FEA analysis. Everything is available in one easy to use, intuitive UI. Because SimScale is cloud-based, this opens up many possibilities for real-time collaboration and support. If I want to share a project with Richard, all I need to do is put his email address in, and instantaneously we can both be accessing the same project from anywhere in the world with an internet connection. There's no need to transfer large data files or transfer simulation projects. This also means that we can provide unparalleled support as well. Our support engineers can immediately come into a project if you give them access and give you hints and tips and help with your simulation. And we typically provide support within a few minutes of the question being asked. Also, because SimScale is cloud-based, everything is completely scalable. This is critical for AI-based machine learning algorithms because from one day to the next, you might be running a standard FEA simulation one day in SimScale. The next day, you might want to be able to run thousands of simulations in parallel to set up your AI training data. With SimScale, it's completely scalable and possible. You don't need to switch on any HPC license or make any changes. You can immediately scale from 1 to thousands of simulations a day, running in parallel. And SimScale is cost effective. Obviously, this is important for many organizations. There's low CapEx, low cost of ownership. There's no HPC to manage. There's no expensive hardware to distribute and install. So it makes it very viable to scale from 1 to thousands of users. Okay, so they're the broad capabilities. I'm going to hand over to Richard now to cover the AI piece in a bit more detail. Thanks.
Great. Thank you, Steve. Great introduction. Yeah, I want to maybe take a look now at AI and why are we even here to talk about AI? Why do we need AI? And in the end, it comes down to the requirements of today's engineering organizations, right? What challenges are they facing and what tools do they need to get the job done? And we have many customers and they come to us with questions, problems, and we try to help them. And it's just a sample list of issues that are in today's engineering organizations we're trying our customers to help with. First of all, optimization needs, right? They have been there since engineering started, and they're not going away and just getting more requested by the day. So we need to reduce manufacturing costs, reduce energy, material consumption, CO2 footprint in general. So many levels of optimization requirements are present. Then we're starting a new era of generative design. So there's a lot of tools come available that can generate thousands of CAD models instantaneously, right? But that means we need a matching engineering tool that can actually evaluate these thousands of models. Otherwise, we're just generating data without any use of it. We have more and more design criteria, right? IoT becomes a part of any device. So there are new criteria coming to devices that have been designed maybe since decades, right? We need thermal management, vibrations become more relevant, environmental exposure, electromagnetics, and so on. There's a trend in mass customization from products that people wear to the construction industry. Every product or a lot of products become mass customizable, and we need engineering tools that can be operated with the specific requirements of these requests. And then we have obviously something that we have been talking since here. Digital twin has been a buzzword in the industry since a couple of years, but now it really becomes reality. So people want to generate digital replicas of real-world products, monitor the performance, optimize it, detect anomalies, and all that needs to happen in real time. Otherwise, it's not effective. So, and that's why we need specific tools, and one of the solutions might be AI that help us solve all of these requirements to be fast, efficient, and to be deployable at every stage of the design process, from very early stages, from the generative design stage to the last monitoring operational stage, like with the digital twin. And now, how we see this happening and how we implement it at SimScale is, SimScale is a tool or a platform that has several layers. On the bottom layer, we have the infrastructure, right? We have the HPC environment, user, data management, process management. We can manage all the simulation workflows. And on top, we have simulation methods. We can import CAD models, we can mesh them, we can solve with the PDE solvers, and we can post-process the data. And exactly here is where we see an AI solution to take place next to the PDE solve as an alternative to running a full solution with tools that we have been knowing since decades in a new form that provides us instantaneous feedback on our design decisions. And orthogonal to that, we have the specific physics, the applications that we want to solve. Right? So the AI solver are below that. It means that they're orthogonal, and every physics that we can simulate on SimScale might be supported and accelerated by an AI solver. And fundamental in the end, be presented to the user with different means. The standard one is the workbench, where people can set up manually all the workflows, solve the simulations, but also with the web API, so they can script specific workflows, parametric studies, and so on. And also very important, it can be integrated in third-party tools. So it can be directly integrated in existing design workflows. So we hope that with this solution, we can solve all the major aspects of today's design challenges. And we cannot do it on our own. That's why we have here Jakob from Navasto. They're the experts on machine learning, on our AI solution that we have together brought to the market or doing this today. And therefore, I want to invite Jakob to let us give us an introduction to Navasto, what you're doing, and how your solution is transforming the way engineering is done.
Thank you, Richard. Yeah, thanks for the introduction. And we at Navasto, we accelerate engineering processes. And the company Navasto was founded in 2014 by 2 engineers, and now we are over 20 people from the fields of engineering, physics, computer science, software development. And within these 10 years, we worked a lot in process and method development and computer-aided engineering, and we saw the growing potential, how these engineering processes really can benefit from the use of machine learning functionalities. And that's why we developed this API, NavPack. It's like a library for all the functionalities you need if you really want to use AI, so to say, to do what you want to do, just faster and maybe a bit better. And we developed this vision. It's like a picture in my mind when I think about AI accelerated engineering, that people from different disciplines and from different departments, they can meet in one room and make decisions within this meeting, and they do not have to postpone to another weekly meeting because they have to wait for new designs or for new results, which kind of evaluate the performance of this design. And I think, I mean, maybe some of you also experience this pain of this serial process, of this iterative process, which just takes too much time. So this is kind of the picture I have in mind. And a possible result could look like this. So imagine a designer and someone from the aerodynamic department, they meet in one room and they work within, for example, Blender to create new designs and instantaneously evaluate the performance of their design changes. So you see the drag prediction on the lower left corner and also the velocity prediction for this design, and then you just simply start working. You start working on the geometry. Just manipulate edges and vertices, points, faces, and you're completely free. And the new input is the new geometry of the car, the new shape, and you get instant feedback within I don't know, the fraction of a second. So you can really work out different designs, test out different things, and yeah, at the end, hopefully come out with a better product, or yeah, the results you need to make decisions. And you're completely free to, I don't know, translate, rotate, manipulate all the shapes and get the feedback as expected. So this is kind of the end result. But if you want to do something like this, it's a two-phase process which needs to be done prior to an action like this. So, and the first step is always the model training. So since this is a data-driven method, obviously you need some input data. This could be data from a certain project you worked on. It could be also something like called legacy data. It could be data which is lying around in your simulation database from the last 5 years, something like this. So you take all of this data and train a machine learning model out of it. At Navasto, we use different methods. Most of the time, it's a GNN, a graph neural network, which we train, which is really smart and really beneficial for most applications. But we can also train other methods. This really depends on the use case. Something like a PCT, a point cloud transformer, or convolutional neural network, CNN, or simpler methods like a reduced order model, which is basically a POD approach. So once you train the model, the best model possible for your application, you can then use this model. So you just create a new input, like you saw, using Blender, do it in SimScale, CATIA, whatever tool you're familiar with. And you can not only create or use shapes as input, you can also mix and match this with parameters you designed in projects, since a lot of projects really rely on parameters. Then you give this input to the model, and then you get information about the scalar performance values, so-called KPIs. And not only them, you also, as you saw, get information about the flow field and also some sensitivities. And these predictions are then really, really fast, so you can get instant real-time feedback when you really want to work with it. So maybe some use cases. So like this is a foiling catamaran from the Sail GP, which is something like the Formula One of sailing. And this catamaran is defined by 8 parameters, which change the environmental conditions, like the wind speed, the wind angle, but also something like sailing settings. And it's an example from the maritime world. So people look at the pressure distribution on the sails, obviously, to also calculate these forces. So you can really play around with all these parameters which define the sailing conditions. You get the instant feedback on the surface pressure and also on the scalar values, like pointed out on the upper right corner. And this is another use case. It's really testing thousands of geometries, also involving the volumetric flow field like this, and really finding optimal configurations. So the real benefit is that you have, basically unlimited iterations to really reach a goal and to be competitive without running thousands and 10,000s of simulations. You just need around about 100 simulations to build a model, and then, as I said, run thousands of predictions. The nice thing is, since this is purely a data-driven method, you can use the same methods for different applications. You do not have to stick with external CFD. You can use it for crash simulation, like shown here for a Toyota Camry, which is driven against the wall. And you see the development of the geometry and also the plastic strains here. So you could say, okay, when I don't know, change the thickness of my A pillar, the situation would look like this, and you get instant feedback for something like this. Another application could be also that you train on samples like the heat sink, which is a conjugate heat transfer simulation. So what you want to do is define the best possible geometry to have the best possible heat transfer in this device. So you can test around again different scenarios, different designs, and you could either run a simulation like seen on the left-hand side, or do a prediction within seconds, and you see that the results are really similar for unseen test data. This is one thing, and I think sometimes it comes in handy if you have something like surface field predictions or volume field prediction, but sometimes it really comes down to scalar values. This is, I would say, most of the time in engineering processes, this is really a hard performance indicator, and it needs to be addressed. For example, like this, it's just a test case on a so-called driver car, which is a mix of a BMW 3 Series and an Audi A4. So where you just test on adding a spoiler, optimizing the spoiler position, and also in addition to that, change basically everything on the car. And once you trained your model, you can make predictions for new input geometries, like you can see on the right-hand side. And this is a so-called calibration plot, where you simply compare the ground truth, which would come from a CFD simulation, to the prediction quality for the drag prediction. And you see that the mean absolute error is around about 2 drag counts, so it's below 3 drag counts. So this technology can really improve the way people work together. The accuracy is as good, I mean, obviously as the input data is, but it's really usable on a daily basis. But to reach results like I showed you in the last few slides, you need to really establish a good process, which has, I would say, the basis for this process is a classic simulation workflow, like you can do on SimScale at the moment. So you have an input, a geometry, parameters, whatever, then you give it to the simulation workflow, and then you get your results for scalar values, flow fields, surface fields, something like this. And when you want to add this AI accelerated workflow I showed you, where you can make predictions within seconds from an AI model to get more or less the same results or comparable results, but only in real time, then it always comes down that you need to select. You need to select whether you have a suitable model for this input you just generated or not. And if the input is not there, or let's say that your model has never seen an input like this, so it would be pure and hard extrapolation, which is not good, then you cannot trust your prediction quality. You need to run a simulation, and you need to feed back the simulation results to the AI model to update this. And I think this is the perfect match between Navasto and SimScale, that within the SimScale platform, you really can do both. And as Richard said, just run 100 simulations fully parallel, train your model, that next time you come to this selection process, it's a clear thing. You can benefit from the prediction quality and from all the benefits I showed you, good accuracy and the speed and unlimited iterations. So this is again why I think it's really nice, and I'm super happy that we now established this within SimScale.
Yeah, awesome. Great overview, Jakob, and I really like the use cases. Very interesting applications. And now, let's get back to SimScale and see how can we take this know-how that Navasto has built over the last decade on machine learning models on SimScale. And just to repeat a bit on the workflow, right, and to zoom in how to define a machine learning model and how to use it. and how it will be on SimScale. So first of all, as we've seen, the first step is always to collect the data. So you can either use existing data or you can generate synthetic data, right? On SimScale, this will be very easy, as your data is already there in your account. You can just use it as it is, or you can also, with parametric studies, with the help of the AI, easily generate hundreds of models in a very short time to generate synthetic data, from which you can then build the machine learning model later. What is the also a very important step is in traditional workflows for machine learning is you need to collect all the data you have on your models, somehow clean them up, and put them in a central place where you then can run the training, right? So this is the data preparation phase. For SimScale, this is not required that you download any data. It's already in the cloud. It's in the same HPC system where the training is happening. All the data sets are 100% compatible, right? They're all run within SimScale. They have specific requirements met, so each and every model can be translated in the specific input that is required. At the same time, all the data is secure and safe according to industry standards. Once you have the data collected and prepared, right, you can train your machine learning model, right? So we're using basically on the back end the methods and solvers, more or less, that are provided by Navasto in a very transparent way to the user. So there's no additional infrastructure needed. We can already use the existing SimScale infrastructure, existing GPUs that we can also use for lattice Boltzmann solver. We can use it also for the training, and that's what we do. And we have automatic report generation on the quality of your machine learning models. Once you have the machine learning model trained, it can be deployed to your users, right? To the users of your team members, for example, and this can be done in a very fine, granular way. Right? We have full access control, version control. We can deploy the machine learning models publicly or privately to specific users only. Right? And at the same time, we have the full digital thread in a sense of which models, which simulation results were used to build one specific machine learning model. So we have traceability and reproducibility. And finally, when it comes to using a model, right, every user can decide when to use an AI solver to solve a problem, when the main focus is on speed, right, when there's a very specific use case, and when we have the quality criteria met, right? So when we say, okay, it's this prediction is within the scope, as Jakob said, of the data that was used for training and not far away, then we can use it. But if you have a case where we are far away from data that the model has seen, it's very easy on SimScale, just use the normal PDE solve, right? So every problem that can be solved on SimScale can be solved either with a machine learning model or with a full PDE solve. And I think that's the real strength, right? Where you can decide on the spot, do I run a machine learning prediction or a PDE solve? And if I don't trust the machine learning prediction at any point, I can just run the PDE solve to be assured that the results are accurate. And of course, what I can do then later is, once the PDE solve is done, I can use this data and feed it back into the machine learning model and retrain it, enhance it with the newly generated data. So the next time, I'll have already a better model. Now, let's actually go to the meat of today's presentation. What do we have? What do we have to offer to you when you want to use machine learning on SimScale? So the first product release that we'll have is an AI preview. That means while setting up your simulation, you get a preview already of your simulation result. You can play around with different geometries or different load cases, and you instantaneously, more or less, will get feedback on the results like displacement stresses, velocities, pressure, whatever the specific analysis type is. The initial models that we're having now are centrally trained by SimScale and are very application-specific models. What we have already done is have the centralized training infrastructure that is physics agnostic and fully integrated into the SimScale platform and infrastructure. So any new model can be easily set up, trained, and evaluated. And These models can then be released to users in a public, but also in a private mode. And that's what is interesting then towards the end, where we want to invite you to really come to us with your use cases and let us work together to build an AI model for your use case and to actually privately deploy it only for your user. So your data is safe, but you can already evaluate machine learning models powered by Navasto and SimScale on SimScale. So on the right side, we see one of the first models that we've done with this machine learning solution, which is a centrifugal compressor, so a compressible CFD analysis, where we see on the left side the prediction of the total pressure, and on the right side the original CFD results. So these data sets that you're seeing here are the ones that are not seen by the machine learning model during the training. So these are unseen test samples. And what we've varied during the training is the different blade geometries, different thicknesses of the blade, different shapes, and different blade numbers, and obviously also different flow rates through the pump. So I don't know exactly, I think 230 models were used for the training. And here we can see already visually how well the results of CFD and AI prediction are matching. So now let's go back to see what actually we have on SimScale and how this works. So I'll introduce first, this is what you're seeing here is the SimScale workbench and the dashboard. So you see your projects, the projects of your team that are shared with you. You have folders. In the folders, you can organize multiple projects, and you have certain details that you can already see here. And once you're confirmed that that's the project you want to work with, you open it, and you're landing inside the SimScale workbench. So we already have here a solved model, not just that we have the reference data as well available for later. So it starts always with the geometry. We upload the geometry in a generic file format. All the relevant formats are available. The first step, we can edit the geometry in SimScale. So we can change the shape, make it thicker. If the geometry is already done or okay for simulation, we can select one of the analysis types that we are having available, CFD, FEA, and soon to come a small teaser, electromagnetics. Now we create a simulation of the type that we are interested in, a linear static analysis. And we load the template. So on SimScale, we always have a templated workflow and follow it from top to bottom. First red spot is the materials. So we add the material, in this case, steel. So this connecting rod should be of steel. It's just sample model because this is our first tutorial that we ever had on SimScale 10 years ago. So now we fix one side of the rod. We select all tangent faces, that should be fine. And then on the other end, we just put a force. Right? To make it simple, we put a force on two faces here on the hole in the upwards direction and the y direction of, let's say, 500 Newton. And now our simulation setup is complete. Now we could start the actual simulation, but now look here on the top right, we have AI preview. So we click it, we see that there are several models available, and we select one of the connecting rod models, in this case, the POC. And then at this point, the model is evaluated. We're tessellating the geometry, sending it to the ML model, evaluate it, and get back the results pretty fast, less than a second. We can check the von Mises stress as a result, because that was one of the quantities that was trained for, also the displacement. And now we can play around with different load cases, for example. So we added a force in the Z direction, and we see a different shape with the von Mises stress, much higher values. Now we're at 150 megapascal. So yeah, we might wonder if the high stress is actually coming from the side force. So we remove the Y force again, run the new load case, and actually check how high the forces are now. Actually, we can confirm on the side force already we get 100 megapascal. And so this is just a quick example how we envision these machine learning models to be used. Either vary through different load cases or vary through different design options, or both at the same time. So now at the last step, we want to actually see how accurate are these predictions. So that's why we had here already some predefined results. So this is now the use case on the right, the simulation result on the combined use case 500-500 in Y and Z. And let's open the result and see if they roughly match. So we can already see the patterns look very, very similar. The peak stresses are also in the same spots, and also the ranges are pretty close. Now let's have a look also in the other model. So just to check if you're also fine here. And just to be clear, these are not super complex models to run. But in the end, for the machine learning model, it doesn't make a difference if the original model was taking 5 hours or 5 minutes, because it will always be fast to evaluate. And it's totally independent from the original simulation time. So here we also see very, very similar results. So let's get back to the presentation, to the last step to look in a step ahead. Where are we heading? So we have seen AI preview. So while you're setting up your simulation, you get instant feedback on how the results will look like. And the next step will be a full AI solve. It means we have a completely equivalent solver and result and behavior if you run a full PDE or an AI accelerated solve with full API support and the support to integrate it to third parties. So this will enable machine learning enhanced workflows in other tools as well, powered by Navasto and SimScale. Additionally, what we will enable is self-trained and self-managed AI models. So you, as a user of SimScale, if you have already data in your account, or you train or you generate new data synthetically with a script or on a platform, you can build your own machine learning models on your use cases. Right? You will have the tools to select the specific simulation runs for your training, to filter by specific analysis type, by specific result types, settings that have been used, and then you can actually run the training and also deploy your machine learning model results to your colleagues in your organization, or if you want, make it public. And finally, you will have a full digital thread of all the data that was used to generate a specific machine learning model. So once you update it, you can give it a new version and look back on how much the model improved in predicting your results, or maybe it didn't improve and you can go back to the previous version. So that's how we see our trajectory in the next year to really enable self-managed machine learning models directly in SimScale to democratize more or less machine learning in engineering. And with that, we are done with the main content. I'm really happy to answer any of your questions, and also Jakob, just feel free to pose your questions, and in the end we'll have a quick final slide.
Yeah, great. Thanks, Richard. Thanks, Jakob, as well. I think I speak for everyone here that was extremely exciting. I've been with SimScale for about 3 years now, and this is one of the most groundbreaking, incredible things I've seen us doing. And with the questions we've got coming in, that seems to be the thought on everyone's mind here as well. There's a lot of questions. I don't think we'll have time to answer them all, but let me group a few together here in one question. We've got a lot of people asking how much data is required. You know, where's the data coming from for these models? So as an example, Richard, how many models were required for this connector rod demo?
Mm-hmm. So yeah, first of all, it's very vastly different how many models are needed, how many data points are needed to predict. I think maybe Jakob can talk about that in more details. The connecting rod was a very simple model. We used less than 200 data points to train it. And also depends on the range of values you want to train it for, right? if I want to train for arbitrary sets of boundary conditions, which might even not make any sense, I might need to add more data to the problem to also capture these senseless summations. But if the more defined my problem is, the less data I need to get to the same level of quality in the results.
Okay, great, thank you. There's quite a few people asked how the recording will be shared. If you registered for this webinar, the recording will be sent out to you once it's available. Usually takes 1 to 2 days for us to prepare and send that out. Okay, someone's actually asked specifically with the connector rod, how the training data was prepared for that model. So you said how many simulations, etc. So what's the process for actually building up the data set that's needed?
Yeah, so the connecting rod was very simple. We built a script that created on SimScale with the API the 200 or so simulations. They run more or less in parallel within a couple hours to build the base data set. Then we had another currently background thread that basically collects these models, puts them in a bin where they're then used for training. We have a model manager and an AI model manager that then basically takes the generated models and deploys them to the users. The models will not appear everywhere, right? So we have now this connecting rod model. Obviously, if you run an incompressible CFD in a pump, you will not see the connecting rod, right? So it has a specific scope of being shown and being available to the user, and then only when it makes sense, they can use it.
Perfect, thanks. We've got another question come in asking about how this actually differs to running a simplified 2D simulation. I guess what they're getting at is you could get very quick results if you simplified a simulation to a 2D model and ran that rather than an AI prediction. So what do you see as the key benefits to the AI prediction compared to that traditional approach?
For me or for Jakob?
Jakob, would you like to answer that one?
Yeah, sure. I'll be happy to answer this one. I think, yeah, as Richard also mentioned, it makes no difference. I mean, the connecting rod is really just an example, like a tutorial. But if you imagine you really run a high fidelity simulation of a complete car, external CFD of a car, so you can run a DDS simulation which takes, I don't know, 15 hours on 1,000 cores. It really takes some time, and it makes no difference. So you can get predictions which are based on high fidelity simulations if you use them as an input for the training. So I think this is this is really the advantage. Whereas if you use simple 2D models, something like, I don't know, potential solvers, something like this, you have the low fidelity simulation all the time in your complete process. And if you want high fidelity results, you need to simulate them. Yeah, I think this is maybe the difference. And
yeah, maybe as an example of FEA, right? So this is now linear static analysis, but you can apply machine learning models also to nonlinear models, right? And there you don't have the same analogy anymore that, yeah, I maybe can just run a simple FEA, which also takes only a couple seconds most of the time, right? To get an estimate of the results. There you're in a completely different range. And then you actually see large differences in the results, but still the same runtime of the machine learning model, because it's the way how it's evaluating the results is always extremely fast and efficient.
Great, thank you. So unfortunately, we haven't got time to answer all of the questions that have come in, but we will get back to you with a message, with an email after this event if we haven't managed to respond to you yet. So the final point that we want to cover is, if you like what you've seen today, if you're curious, if you're interested to actually build your own models, please get in touch. We have an early access program, and this means that you can actually share your data with us, and we can look at building AI machine learning based models for your data to make models available to you and get you set up and using this as early as possible. Okay. Anything else to add on that, Richard? The early access program?
No, just don't be shy. Reach out to us if you have a use case in mind that makes sense from your point of view. We're really happy to learn. We have now this technology, but we really want to see this in the hands of customers, of actual users, what they can do with it. And yeah, we're happy to take your case, run it on SimScale, generate a machine learning model, deploy it for you. You can test it out and give us feedback so we can learn and make it even better for the next webinar, when we hopefully will be presenting the full AI solve.
Perfect. So yeah, thank you again to our partners at Navasto and Jakob for presenting, and thank you again to Richard. Thank you all. Goodbye.
Thank you.